All right, everyone. Welcome to a new setting. We're here in my fabulous garage where I happen to remember that I had a whiteboard that hasn't been erased in a while. For about 2 or 3 years, there was some work of art affixed here semi-permanently. You can see sort of the remnants of a volcano here. There was a poop emoji somewhere. Managed out right there. There's the poop emoji, a little schematic of a family right there. Probably from that distance you can't really tell. You can see that somewhat. I did my best to erase this so I have a surface at home that I can work on. So we're going to talk a little bit today about section 5.3 from our book, which is just sort of continuing further examples of mathematical induction. There is a little discussion at the start of that chapter, or that section rather, talking about the difference between deductive logic and inductive logic, and how induction is in a sense really deductive, but can be used to prove claims that we discover inductively. And what I mean by that is looking at a set of data, a set of information, maybe some examples that give rise to a particular pattern. And then that pattern is something we can prove by mathematical induction. Inductive logic is going from specific to a general statement. So if you observe a pattern, a general pattern that appears in specific data, you're exercising inductive logic. And once you've made that pattern, or that observation rather, you can prove that it's true, often using mathematical induction. So we're just going to do a couple more examples together. I'll give you another one to think about on your own, or to work with remotely. You can talk about it in pairs if you want to schedule a hangout. You can talk to me about it if you want to schedule a hangout, or talk to Stephen about it. We'll all be accessible to help you. So just a couple more examples of induction, and then you should be ready to tackle a few more problems. I'm not going to have a quiz, by the way, at the end of this section. No quiz on this section, but there will be on section 5.4, which I'll post a video about no later than the end of the week. So just a couple quick examples about induction, looking for patterns. These are all going to have to do with the idea of divisibility or summation, some of those ideas we talked about in section 5.1 and previously. So let's see if we can find a pattern in sums of the following form. So we're going to start with 1 over 1 times 3 plus 1 over 3 times 5 plus 1 over 5 times 7, and so forth. So all we're doing is looking at reciprocals of the product of two consecutive odd numbers. And it takes a little bit, it might take a little bit of thought to find a pattern for such sums, but this is what it turns out to be. I hope you can see that. Please let me know. Just respond to me by email or shoot me a text or something. Let me know if this setup is going to be visible to you. I know there's a little glare right here. So this is the general pattern for such a term. You'd have 1 over this, of course, is an odd number. Anytime we have an even number, minus 1, 2n minus 1, and then the next odd number would be 2n plus 1. So this formula captures that general term that we're trying to get a hold of and describe. So we sum up all of the reciprocals of the products of two consecutive odd numbers. Now, if you work through the details here, we can compute the first few examples. So when n equals 1, rather, our stopping point, 2 times 1 minus 1 is 1, and 2 times 1 plus 1 is 3. And that's the only term we have present. So when n equals 1, we just get 1/3. When n equals 2, we get 2 terms. A 1/3 from the previous, and 1/15, 1 over 3 times 5. And if we find a common denominator, and we add and we simplify as far as we can, it looks like we end up getting the fraction 2/5, if we do our math right, which I think I did. Let's just do one more to see if we can come up with a pattern. So this is the n equals 2 case. The n equals 3 case, we have the two terms we already saw previously, 1/3 plus 1/15. Now we add 1 over 5 times 7, or 1/35. And I can use this already since I've already seen what the sum of the first few terms is. I just add 1/35 to the previous one, find a common denominator by multiplying this by 7. Looks like I'm going to get 15/35. I've got a common factor of 5, so it looks like I get 3/7. in the case of n equals 3. So already you might be able to see something of a pattern here. You've got 1/3 to start with. Let me circle these so we can see them. We've got 1/3, the n equals 1 appears here. N equals 2, the 2 appears in the numerator. N equals 3, similarly. So it looks like our numerator is always going to be n. And we even have a pattern in the denominator. This takes practice to see these patterns, so if you don't see it right away, that's fine. But in the denominator, it looks like we've got 3, 5, 7. It looks like it's the odd numbers that are going up, starting with 2 times n plus 1, 2 times n plus 1 here as well, 2 times n plus 1 here, and so forth. So our guess for our pattern is that this, and I'm just going to call this quantity, I don't know, I'll call it S sub n for sum, S for sum. S sub n, just because I'm being lazy, looks like it might be n over 2 times n plus 1. So we're going to go ahead and guess that as our formula and see if we can prove that by induction. So proof by induction. Remember, it's never a bad idea to remind your reader what method you're using for your proof. Our proof by induction will have 3 steps, as we've seen before. We have our base case. And in this case, it makes sense to start our summation at n equals 1. We already have the formula n equals 1. So when, I think we were using k, right? So when k equals 1, the left-hand side, actually we've already computed this because the left-hand side, our left-hand side is S1, which we've already computed is 1 over 1 times 3, or 1/3. And the right-hand side is similarly just plugging into our formula here. 1 over 2 times 1 plus 1 is 1/3 also. So the base case holds. Base case is true. And remember, in an inductive proof, the next step, sorry about the garbage can right here, by the way. The next step in an inductive proof is the easiest. It is just to make the inductive hypothesis. And that's to assume that P of k is true for some k. And remember, this is our generic particular, our fixed but arbitrary k. And in this case, that means that Sk is equal to k over 2k plus 1 for that particular k. Now, the last step of the inductive proof is to go to try to use this fact, use this assumption to prove the k plus first case. And remember, this is kind of like dominoes. The base case knocks the first domino over. The inductive hypothesis says that if you knock over the kth domino, there's no gap between the kth and the k plus first, so everything kind of collapses and continues a chain reaction. That's the idea behind induction. Start with the base case and use the coupling of the inductive hypothesis and the inductive step to proceed from the base case to any value of n. All right, so knowing that that Sk is k over 2k plus 1, let's make our inductive step. Our inductive step, we must show that S sub k plus 1 is equal to k plus 1 over 2 times the quantity k plus 1 plus 1, because that's what this formula looks like when k is replaced by k plus 1. And just so we're clear, if I distribute the 2 here and I simplify, I get k plus 1 divided by 2k plus 3. I've just realized that I do not have a little rag to clean this off with, so I'll be right back. Ha! I'm gonna have to get some cleaner for this later. In the interest of time, what I might do is record this single example and then come back and do a second video, part 2 for this section, because I've got some bagels in the oven right now that I need to make sure I get out before they burn. So, in the interest of time, let's finish off this example and then I'll post part 2. All right, 2 different videos, same content for section 5.3. So, we're in the middle of the inductive step where we're trying to prove that the sum that unfortunately I just erased has the form k plus 1 over 2k plus 3 in the k plus first case. Now, just a reminder, sk plus 1, unfortunately I just erased it, but I'm going to write it slightly differently, only slightly. I'm actually going to write it highlighting the second to last term as well, because this is the last term when our value of n is replaced by k. When I replace that value with k plus 1, I get a slightly different value. Notice all I did here is I made n equals k plus 1 for my last term in the series. Or the last term in this sum, rather. So for the last term in this sum, I replaced n by k plus 1. Now we saw this pattern already. All that's going on when you go to the next term in the series, in the sequence rather, all you're doing is you're taking the previous term and you're adding one more. The previous sum, and you're adding one more term. In other words, this whole thing to begin with is really just sk. It's what we had stopping at the value n equals k, and then we're throwing on this last extra term. And that extra term is pretty easy. We can simplify that a little bit too, because we could distribute, just like we did down here, distributing k plus 1. We can do the same thing here. This is really 1 over 2k plus 2 minus 1, which is really 2k plus 1. And this here is really 2k plus 2 plus 1. I hope that's clear. 1 over 2k plus 1, quantity times 2k plus 3. So all we have to do now is show that this sum, sk plus this, winds up simplifying to that. And I think we can do that because we already have a formula for sk. That's the beauty of induction, is we have assumed we know a formula for sk. So by inductive hypothesis, we already have a formula for sk. Let's use it. Sk plus 1 is going to be sk, which we already know, plus this additional term. And there's a really nice fact here that we can make use of. Notice both of these denominators have 2k plus 1 in them. So all we'll have to do is introduce this part of this denominator over here when we're finding a common denominator. So let's do that. We'll multiply this fraction by 2k plus 3 divided by 2k plus 3, so we don't change things, and that'll give us a common denominator. In other words, if I multiply this first fraction, by 2k plus 3 in both the top and the bottom, I get a common denominator. I can just add 1 across. Now, here's my eraser here. I'm just going to erase this computation so I have a little bit more room. Hopefully I won't have to erase any further. Now, get rid of this line just in case. Clear out the base case. Now we just do a little bit of algebra. Multiply out. And I'm going to leave the denominator alone. We could multiply that out, but there's no need to. In fact, we'll see in a moment, it would have made our lives harder. Because in the top, this is where I just use a little bit of foresight. If I know the formula I'm trying to get to, I suspect that I would really like to be able to cancel this 2k plus 1. And that gives me a hint that maybe the top, if all is fair and perfect in the world, maybe the top has a factor of 2k plus 1 in it that I'll be able to cancel. And in fact, if I factor this, if I look at this and I think about what times 2k plus 1 might end up being 2k squared plus 3k plus 1, again, we could use some foresight. We suspect that it's k plus 1. Let's see if that's really the case. Does 2k plus 1 times k plus 1 really multiply out when we FOIL this? Do we FOIL this and get 2k squared plus 3k plus 1? I think we do. Because 2k times k gives us 2k squared. 2k times 1 gives us 2k. 1 times k, doing the inside terms, gives us another k, and all told that gives us 3k. And finally the last terms, 1 times 1, gives us 1. So if we FOIL this out, we get this product, which means we get this factor going the opposite direction. And that's perfect, because that enables us to cancel those common terms 2k plus 1, and in the end what we get is k plus 1 divided by 2k plus 3, which is what we wanted. That's the end of the proof. And just as a reminder, we start out with the base case, we prove it's true for the first case, we then make the inductive hypothesis that if we can prove this case, going to the inductive step, we'd love for that to be able to knock the next domino down and be able to prove the 2k plus 1, or sorry, the k plus 1 case. So we started with the base, our starting point. We made an inductive hypothesis and then showed that based on that hypothesis, we can always knock the next domino over. And in the end, we ended up getting a formula that we conjectured was true. Now I'm going to stop the video there at the end of this example, and I'll do a second video with another example, just so we're getting a little more practice with induction after I get the bagels out of the oven.